So this is what I mean by what's happening to the solution. I think it's also really nice. I want you to be able to think like that. It takes time, but it's a good idea to get adjust to that. So it's written again, Chinese remainder theorem. We thought we all understood that, and here's the version. N and M, those are two modulus, relatively prime. And we're defining a function, right? So we're using this fancy congruence class, Z and M. Or you can look at it as a Z mod 6, and looking at the 6 as 2 times 3, right? So that's like that. It's the domain. What is the codomain of this function? Z mod n, right? Cross Z mod 3. And here, Z mod n cross Z mod 3. Right, what does this cross mean? This is a Cartesian product, right? How the elements looks like in there. It looks like 0, comma 2. 2 is a congruence class there. 0 is a congruence class there, right? If you really want to distinguish, you have to put 2 and 3 there. But knowing that it's in the first slot, you already know it's coming from congruence mod 2 class. You already know congruence 3 class, right? So bracket means slightly different. So feel comfortable with the Cartesian product? Every pair, you put it in there. All right, that's that and that's that. Let's understand function. What is the function saying? You pick an arbitrary element in here. How does the arbitrary element look like? Maybe 4. Make sense? Class that contains 4 in them, but Z mod 6. So where did that go? Pairs, right? It goes exactly to 4. Goes just to 4 in there and goes exactly to 4. That's the definition. Send it exactly the same number. Use that same representative. But like he said, this is actually 0 class. That is actually 1 there, right? You end up sending it there. Okay? So do you see the solution of Chinese remainder theorem? There's some number out there called 4, which is congruent to 0 mod 2, and here is congruent to 0 mod, 1 mod 3, right? That version is kept like this, captured like this. So if the Chinese remainder theorem proves which part of this map, surjectivity or injectivity of this map? According to the description of our Chinese remainder theorem, does that prove this map is surjective or is this map is injective? Surjective goes like this. Choose any pair here, then there must be a 1 in there. Injectivity goes, if you choose 2 elements in there, and they go to the same thing, they must be in the same element in the first place. So how does the Chinese remainder theorem go? First, you look at these congruence classes, right? Different congruence classes, like 2. That corresponds to 1 element in here and 1 element there, right? And it says there is a solution there. So which one is it? It's a surjectivity. Yeah. The Chinese remainder theorem proves that F is surjective, right? Choose any element, X is congruent to A mod N, congruent to B mod M, right? Then that corresponds to class A in Z mod N, class B in Z mod M, right? But there is always something out there going to hit that if it is a surjective, right? So surjectivity is proved by Chinese remainder theorem. Interesting thing happened. How many elements are here? Number of elements. Here there's n elements, right? Here's m elements. Cartesian product. How many? N times m. How many elements are there? N times m. If you have function defined the same number of elements, if you establish injectivity, don't you think it's automatically surjective? So I'm gonna do a little bit of magic in here. Yeah. 2 things going into the same thing, then it has to be the same element in the first place. 1 to 1. That's right. That is the word. That is the word. Yes. Yeah. So look at here. I'm going to prove injectivity. If they prove surjectivity, if they have same number of elements, doesn't that already prove injectivity? If I prove injectivity, because the same cardinality is a surjectivity, the other thing is coming for free. So let's see if we can show injectivity independently from Chinese remainder theorem. Okay? All right, I choose two elements, A and B, integer, then class A and class B is in Z mod NM. I chose two elements, both in Z mod NM. Such that f of bracket A is equal to f of bracket B. Does it look like one-to-one condition? I assume that, and I have to show these two things are the same class came from in the first place. Fair enough? So let's follow the definition. What is this thing in here? It's a bracket A, right? This bracket came from Z mod N, that bracket came from Z mod M, right? The other one, bracket B, right? This bracket came from Z mod N, that bracket came from Z mod M. If they're equal to each other, by comparing the first slot, what do we have? A is congruent to B mod N. That's the first slot. By looking at the second slot, A is congruent to B mod M. This is what entails in terms of congruence so that we understand better from this cryptic situation. All right. Now, what does it say about A minus B? A minus B is divisible by N, right? So can I write N times X, right? How about the other one? A minus B is divisible by M, so it's M times Y, right? What is it we want out of that? M times N, right? So tell me, what is some fancy theorem you can pull out here other than Bezout's identity? Don't tell me Bezout's identity. Something fancier than that, such that... That's right. It was like corollary of a Bezout's identity down there, right? And then it all goes into this big theorem. What was that? Fundamental theorem of arithmetic. If you factor A minus B, it has a prime factor that appear N in there, right? That'll never appear in M because they're co-prime to each other. A minus B factored, then prime factor appears in N, will never appear in M, right? So A minus B had all the prime factors in there, they never overlap because of the coprimality. Fundamental theorem arithmetic says all the prime factor must appear inside A minus B with no duplicates. So I hope you see that follows from FTAR, right? But what does that mean? Going back to our functorial description, is that A is congruent to B mod NM, which says the class of A and class of B is equal in Z mod NM, right? So injective, correct? And there doesn't seem like anything that like we did in the Chinese remainder theorem. We did nothing like Chinese remainder theorem, right? But we established this injectivity, right? Because it's injective and same cardinality, it's a surjective, right? The surjectivity gives you Chinese remainder theorem. Isn't that strange? We proved Chinese remainder theorem without doing any of that Chinese remainder theorem. Nothing. Right? It's a combinatorial trick. Counting gives you sometimes an amazing consequence. Because we counted it, the numbers are the same, gives you this strange consequence. It's always out there. All right? Having fun? All right, what's down there? If you have three factors all co-prime to each other, right? Like Chinese remainder theorem, they split up like that, right? And it is what kind of map? Bijective map. Yeah. Fancier word if you were taking algebra, this is called the ring isomorphism. What we just created is a ring isomorphism. This is a ring, you can multiply and add to all that. Happens exactly the same fashion over here. We decompose the complicated ring into rings that we understand better. So all complicated modulus, because of the Chinese remainder theorem, gets down to this level of prime power. Because if it's a prime power, they all split, all co-prime to each other. So according to the Chinese remainder theorem, all you have to study is this guy. Because if I know that, I can glue them together, retain all the information about the general Z mod n. Because all the Z mod n is, whatever this means, split it into like that. Does that make sense? According to prime factorization, along with the Chinese remainder theorem, Z mod n, whatever the factorization of that is number, they split all the way up like that. So all we have to study is studying this guy. Then we have full information about all general situation. So from now on, from this point on, they focus on studying this guy. This is all they want to study because of Chinese remainder theorem. Yeah. We'll start with this one, right? What is the name of this guy? Finite field. We start with a finite field. That's the fundamental case in here.